In this video, I'll show you how to run confirmatory factor analysis as a complete exercise. So this is the protocol, the agenda for today's video. We're going to build a model. Of course, in the previous video, we talked about exploratory factor analysis, and we done all the reliability and validity of the model, and we done all the tests. Now we're going to talk about confirmatory factor analysis with AMOS. So first we're going to build the model, and then we're going to do the factor scores imputations in this video. In a later video, I'm going to talk about the use of control variables, for example, or the grouping of variance in a causal model, like the configural and the metric invariance tests. But for this video, I'm just going to cover A and B. Having this said, under A, we are going to talk about the model fit. So with the model fit, we're going to talk about CFI, TLI and NFI readings. We're going to talk about the RMSEA, the RMSEA, and the standardized RMR or SRMR. Now we're going to talk about the validity and reliability check and the common method bias for the common latent factor, and then final measurement model fit. So if you recall from the previous example, we have this data set on the engagement on Facebook, and we ran the exploratory factor analysis. And when we ran the exploratory factor analysis, we were able to, for example, get the output. From the output, we copied the pattern matrix, and then using James, I think his name is James Gaskin, StatWiki here, we were able to get the plugin for automatically. It's under the version 26, and you can get the plugin for that here, the pattern matrix builder on AMOS, and I have the steps followed in the previous video. So let me show you what we ended up having here. So we ended up having this model with the affective trust, with cognitive trust, with risk factors, and with engagement here. And now what we need to do is we need to we already built the model, so we need to run the analysis. We've done this probably in the previous video. So maximum likelihood, and on the output we're going to take the minimization history, the standardized estimates, and the modification indices. Let's keep it to 4. And now save and run the analysis. Running the analysis, you'll be able to see the this is the standardized estimates, and this is what we care about. So the first thing you need to take a look at is the regression lines, the loadings on the regression lines. Those are called regression lines. Those lines are projecting into the observed variables. Ideally, you need them to be as high as possible. So a loading of 0.9 is awesome, and 0.89 is awesome. 0.56 is maybe acceptable, but not really. In some resources, some sources, they actually demand the 0.7, but maybe you can get away with over 0.5. But ideally, these regression lines should have a 0.7 and above. So over here I have 0.6, 0.5, and 0.5. Not really nice, but let's get away with that for now. Then I have here 0.7, 0.7, 0.8, and 0.5. 0.7, 0.6, 0.7, 0.7, 0.5, 0.6, 0.6, and 0.75. Well, at least nothing is less than 0.5. And now for the covariance, this is the convergent validity. if you would call it this way. And this is now checking the covariance lines or the loadings, the estimates on the covariance lines is actually tells us if these latent variables are very highly correlated or not. We don't want them to be highly correlated. We want them to be standalone entities. So we favor lower values on the loadings here. So any loadings below 0.8, I believe, let me check just my notes here. Any loadings below 0.8 should be sufficient. So all our loadings, as you can see, is below 0.8, that this is good. Now let's check the model fit, and we check the model fit with the view, the output, and going into the model fit. First thing first is the CFI. The CFI here, the ideally should be over 0.95. We have 0.98, so the higher the better. Anything above 0.98 is 0.9. Like in some sources, they could push it and accept the 0.9 and above, but the idea should be over 0.95. So we have here a pretty much very good fit. Our TLI is over also 0.95. Our NFI is over 0.9. That's not bad. Then going all the way to the RMSEA for this reading, we focus on this value over here should be less than 0.05, and on the PCLOSE should be as close to 1 as possible, so higher than 0.95 is the ideal scenario, and we have this here. So based on the model fit, we have a very good model. I'm not very much satisfied with the loadings here, but let's just get beyond the loadings and just accept them for now. Excuse me. So now the next step would be, after the model fit, we need actually one more thing with the model fit is the standardized RMR, and we find this by going to by going to plugins and go to standardized MR. I read this before. So ideally you won't have anything here. The window would be blank. So what you need to do is you need to run the analysis again while the window is open. And here's your reading. So the reading is 0.0557, which is lower than 0.08, and this is what we're looking for. And this is an indication of a very good fit. Very good. So now that we're done with the model fit, let's move forward to the validity and reliability check. With the validity and reliability check, I'm going to use James Gaskin Excel sheet that he provides on his website over here. You see, yeah, this is where I got it from, and you can get it from resources and Excel stat tools. So get the latest one. All right, so now that we got his validity master, it works just fine. What you need to do is you need to paste the correlation table, paste the standardized regression weights, and paste the variance table. Where do you get these readings from? Of course, from the output. Where's the output? Okay, we need to run the output again. No, we don't. We just take a look here. And you need to go to estimates and to go to scalars. So this is where you find it, on estimates and scalars. Let me just, while I'm doing this video, I get it over with and take a snapshot here and my notes. So basically you need to from the output, you just go to estimates and scalars, and basically you have to copy the regression table. So you go and get the regression correlation table here, and then get the standardized regression weights and copy that here, and then the variance table on K2. All right, so let's do that. Let's just start with the correlation. correlation. Oh, how come I can't copy that? Sometimes this happens. Okay, so this is the correlation table. It's going to copy the whole thing, right? Yeah, here's the correlation table. All right, correlations, and then I need the standardized regression weights. I don't know what's up with my, here, copy, finally. Right, copy that. And then finally, you would need the variance table. Variances over here. So I'm gonna just copy that. Okay, there's something I can't figure out with my mouse. So now you just read here, and that's it. Now I have to say that when it comes to James Gaskin, he's really using very tight measures. So the good thing about this table, the result, is that it highlights any problems. It tells you what the problem is. So I have two problems under the average variance here. And this is a validity concern. And then I have also a convergent validity concern here for the CR. And the CR is the composite reliability. So let me write these. Actually, let me just make sure that these are understandable here for us. So first of all, we have the CR. So we have the CR, which is the composite reliability. And then we have the AVE. The AVE is the average variance extracted. And then we have also the MSV and the ASV, and they are both the maximum and an average shared variance. So there are certain limits or thresholds, acceptable thresholds for each. So yeah, let me check if I have any writings here. Okay. I would like to okay. So I'm going to show you here some guidelines. So if your the average variance extracted is less than 0.5, it shouldn't be less than 0.5. But if you take a look here, I have it less than 0.5, and over here it is less than 0.5. But if it's less than 0.5, and at the same time less than 0.5, sorry for that. If it's less than 0.5, then I recommend that you you take a look at this reference where basically what you need to do is just take a look at the at both measures together, which are the, if you take a look here at the AVE being higher than 0.5, but we accept 0.4 because these guys said that if the AVE is less than 0.5 and the composite reliability is higher than 0.6, then maybe the conversion validity of the construct is still adequate. So this will help me with the first problem, which is this problem over here, that I have a convergent composite reliability over 0.6, but over here it is less than 0.5, so maybe together I will outlook this problem. But over here I have also both highlighted in red according to James Gaskin, but according to this source that I have over here, if it's higher than the composite reliability, if it's higher than 0.6, then this shouldn't be in red, and this probably could be acceptable, but actually not really because it is less than 0.4. But according to this resource, it says maybe we can accept the 0.4 because then we have a composite reliability higher than 0.6. So maybe I have a problem here, and then there's a different way, there's a certain way that we could investigate the problem and try to fix it. For now, I'm just gonna go ahead with the protocol and pretend that everything is all right, and this was over 0.4, and then I will just say that this step is over. This is how we do the validity and reliability check, and these are different measures for validity and reliability in here, which is the CR, the AVE, MSV, the also the max R, and these are our constructs or our variable. This is just a correlation table here between the different factors or constructs. So this is now it for now, and I seems like I don't have any problems here. Only problem I have, I probably don't have a problem here. The only problem I have is with the risk construct. So ideally you need to take a look at your output and check for any outliers and so forth. Maybe we can take a look at it in a different video. But for now, I'm just gonna carry on with the next step, which is the common method bias or the common latent factor. For the common latent factor, also suggest that you use the plugin folders on the James Gaskin's website. As for me, I'm gonna use the version 26 because it's a trial version I'm on, and also I'm gonna use the it is not available on the trial version. I think I couldn't find it here, but I found it on version 24, and it's called CLF, and it's working fine. So get this plugin after you install it or you download it. Let me show you just very quickly. You just show in folder, then right click, properties, and unblock. Then you can copy that and go to your C, users, your user and app data, local, and then go to AMOS development, AMOS 26, and the plugins, and have it there. I already have it there. So now you are ready to investigate this model further. I suggest that you copy this or save as, and do the file save as, and save it as CFA, for example, 1 over here. So I have now a totally new model, and I have different separate output that I can generate out of this. So what I'm going to do is basically I'm going to let me select all and then move them a little this side so that I can make some space to create a latent variable here. And what I need to do is I need to select this latent variable, have it selected. Don't rename it or do anything. Just go to the plugins and common latent factor connector, and this is what the plugin does. It just connects to different factors. So this is what it does. And well, just make sure that you are connected to the data, the appropriate data. And now you can just run the analysis again. What you need to do here is you need to take note of the chi-square and the degrees of freedom and plug this in to the chi-square difference. So over here, this model that we just ran right now, it's called an unconstrained model. And this unconstrained model has the, if you want to take a look here, you can see that we don't have any weighings assigned on the regression lines. The only weight assigned is here by 1. So the chi-square here is 105.5. So plug this in, 105.5. And then the degrees of freedom is 96, in fact. And here's 96, perfect. So now for the constraint model, I suggest that you delete that and then go back again and create a latent variable. This time, right click and name it as common latent factor, CLF again, but because you named it this time, what's going to happen when you select it first and then go to plugins, and then this needs to be selected when you use the common latent factor plugin. Look at the difference here, that you named it, you have 0 weights assigned to the regression lines. Having this set, now you can run the analysis, save and run the analysis again, and now take a note of the chi-square. There's 130 and 113 degrees of freedom, so 130 and 113 degrees of freedom, and this will automatically give us the result. So as you can see, the p-value is insignificant, and this is what we want. So we want an insignificant p-value. So ideally, you will get an insignificant p-value. All right. Finally, let's take a look at the final measurement model fit. Basically over here, you just to check again the model and see if it's all fine. So you just go ahead and go take a look at the model fit again. And here's the CFI, again, it's greater than 0.95. And all these values here, 0.9, and this is TLI is 0.98, very high. Let's take a look at the RMSEA. As you can see here, it's less than 0.05. And over here it is very high. So this is comparatively very good model fit. All right, so the last step, which is step number, or step B, which is imputation of the factor scores or calculations of the factor scores, which is the step just, sorry, it's the step just before we happened. Okay, the step just before we start the structural equation modeling. So over here, we go ahead and go to data imputation and proceed with the model. And we're going to keep it as regression. And basically what this does, I think in a previous video, I already talked about data imputation. You have the original data set, and then AMOS will create another data set called dataset_C, and C here refers to complete. So basically it's going to create another data set that is complete. What does it mean to be complete? I hit impute. It means that when you go and look up the, let's check. over here, data C, and open it up with SPSS. By the way, if you don't have SPSS, and you might get into, you might get some errors. Let me just get rid of this. And here is our SPSS data complete. And what you're gonna get is you're gonna get a case number. This is just a sequence number, so it's a serial number from 1 all the way to the end of your incremented by 1 to the end of the records. And then over here you are getting the factor scores. So if you recall, over here we have factor A trust, C trust, risk, and N engagement. So over here we have risk, C trust, A trust, and engagement. It doesn't matter. They also the software computed the CLF. It doesn't really matter for us. We won't use it anyway. You could delete that if you wish, and put the model back again to normal. So it's possible as well. And here we go. We are done with confirmatory factor analysis. One last topic with confirmatory factor analysis is dealing with control variables. So what to do when you have a control variable like a gender or like an age, and you would like to make sure that the different groups do not or they are invariant. So they don't they are there is an invariance to the results when grouped into these different control groups. So this is a different topic in a separate video, but in general this is how we run confirmatory factor analysis with AMOS, very quickly and very briefly.